All right, so we are moving right along. Oh, this is I need to fix that. That should say week 2 Tuesday, which is today. And we are going to cover probability distributions today. And so I realized in the homework I assigned last week, homework 1, I had a couple questions covering the binomial distribution. And that was a topic that we didn't cover in class. It looks like most of you guys answered those questions anyway, but we'll go over the binomial distribution now. So some of you guys have figured it out. Maybe some of you guys had questions or didn't quite understand everything, but I appreciate everybody kind of putting in the effort or whatnot as far as getting those problems answered. Okay, so again, today we're talking about probability distributions, and basically a probability distribution describes the probabilities that a random variable can take. And so, in last week's lecture, we covered what is a random variable. And we said a random variable is the outcome to some kind of random trial, and that outcome has to be a number. It has to be recorded as a number. So it could be something like, you flip a coin a certain number of times and you're going to record how many times it landed heads, or you're going to pick a person at random and you're going to record how tall this person is. Okay, those are numeric outcomes. And we looked at, how do you calculate the mean of a random variable? How do you calculate the standard deviation of a random variable? And we had these formulas that you kind of had to go through the probability table. And basically, a probability distribution is basically that table where we can look at the outcomes and look at the probabilities associated with that particular outcome. Okay. And what we'll see, is that, for certain probability distributions, certain numeric outcomes are going to be more likely than others. Whereas, we'll take a look at a few examples to see. Okay, let me see. I'm getting a few questions in the chat. And let me just kind of quickly review this. It said, okay, so the lecture viewing quizzes are due before the beginning of the next lecture. So today's lecture, there's a viewing quiz associated with today's lecture, and it's due before, our next lecture is on Thursday. So it's going to be due before Thursday's class begins. So Thursday's class begins at 4, and the lecture viewing quiz closes at 3:59 p.m. So I think that's just about as much maximum amount of time I can give you as far as watching it before the thing. Okay, I will drop one view quiz. I will drop one view quiz is the is how it is. Not two, just one. Okay. Not the lowest weekly quiz. No, none of the. All right, so there's a bunch of stuff popping up in the chat. So let me just kind of address these things. So today's the view quiz associated with today's lecture is due before Thursday at 3:59. The view quiz associated with Thursday will be due before Tuesday at 3:59, the following Tuesday. So you have basically like 46 hours for today's quiz, and then you've got about a little less than 5 days for the for Thursday's quiz. Okay. Yeah, so we had 2 view quizzes last week. You're going to have basically 2 view quizzes every single week, with the exception of week 6, because week 6 we have the final exam. So you'll just have 1 view quiz during week 6. I will drop 1 view quiz just in case you miss something or you make a mistake. None of the labs will be dropped. None of the regular weekly quizzes will be dropped. So you can expect probably, the schedule as laid out in the syllabus. So you have homeworks due Sunday evenings at 6. The quizzes will be released Sundays at noon and will be due Monday at 11:59. The labs, there will be 5 quizzes, and then there will be 5 labs, and the labs will be due on Wednesdays at 6 p.m. I believe, is what I've written. Okay. Yes, we did have a weekly quiz. And that was on Sunday. It was released Sunday at noon, and it closed at yesterday, Monday at 11:59 p.m. Okay, I hope that answers your questions in the chat. Okay, so going back to random variables and probability distributions, one example is, what is the probability distribution associated with rolling a die? Okay, and so if I roll a die, the die can land on any one of these 6 sides with equal probability. The random variable will just be, whichever side lands face up. Okay, and so the probability distribution associated with this random trial will be this, right? The outcomes can be any of the numbers 1 through 6, and the probability of any of those outcomes will be 1/6, assuming this is a fair die and each side lands with equal probability. Okay. So we can represent the probability distribution with this table. We can also represent the probability distribution with this graph, all right? And so here we have the different outcomes that are possible, 1, 2, 3, 4, 5, 6. And each of these outcomes have a height, this bar, this little line actually, this line has a height of 1/6, okay? 0.1667 about. And all of these heights are equal height, showing that each outcome has equal probability, okay? Another probability distribution we could have is, let's flip a coin, and the coin is either going to land heads or tails. Now, again, we can't write down heads or tails. That's not going to be a random variable. We have to turn our random variables have to be numeric. So one thing we can do is, rather than just saying, did it land heads or tails, is we can say, how many times do we see it land heads? Okay. And so after one coin flip, we can say it landed heads 0 times, which means it landed tails. Or we could say after one coin flip, it landed heads 1 time, and our outcome would be 1. Okay. So rather than saying heads or tails, we have to turn it into some kind of numeric variable. Okay. And so this would be represented with this kind of probability table, where x can either be 0 with probability 0.5, or x can take on the value 1 with probability 0.5. And again, if we wanted to display this graphically, we can do this. And the scales on the horizontal and vertical axis is a bit arbitrary, but here I have 0 over here, and I have 1 over here, and both of these have a height of 0.5. I think this is pretty straightforward and easy. No surprises here, right? Our probability distributions can get just a tiny bit more complicated, and we can say, you know what, let's flip a coin twice. Okay, so again, our coin can land heads or a coin can land tails. And if we flip the coin twice, we can say, how many times does the coin land heads, right? So again, we don't want to record heads or tails because those are not numeric. We have to record some kind of numeric value. And so we can say, how many heads appear after 2 coin flips? And so if the coin lands tails, tails, then we would have 0 heads. And the probability that the coin lands tails, tails after 2 flips is going to be 1/4. And that's just applying the rules of probability, right? So the probability of tails is 0.5, probability of tails multiplied by 0.5, 0.5 times 0.5 is going to be 0.25, right? We could say, what is the probability of getting 1 head? Okay, 1 head after 2 flips. And there's 2 possible outcomes. We can go heads, tails, or we can go tails, heads. Each of those have a probability of 0.5 times 0.5. So I'm going to add the probability of heads, tails with the probability of tails, heads. Those 2 things add up to 0.5 or 1/2. And lastly, the probability of getting 2 heads, following the same kind of logic and method, we would get a probability of 1/4 as well. So our random variable takes on the value 0 with probability 1/4. It takes on the value 1 with a probability 1/2. And it takes on the value 2 with probability 1/4. Okay, so that will be that would be the results there, flipping the coin twice. And again, graphically, if we want to represent this with the lines, we can do this. So we can get 0, we can get a high 1 with a probability 0.5, or 2 with probability 0.25. Okay, and we have vertical lines here because the other outcomes aren't possible. Okay, as far as the number of heads we get, it's not possible to get 1.5 heads or 1.7 heads or any kind of decimal value. You can only get kind of these whole numbers as far as the number of heads we get after 2 coin flips. Okay, so these are all probability distributions, examples of them. And what we'll take a look at is a specific probability distribution called the binomial distribution, which has a lot of useful applications and is an important distribution for us to learn. All right, before I go on, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter E. E as in elephant. E as in elephant is your first view quiz answer. So that is the week 2 Tuesday view quiz answer number 1 is E. Okay. So, sorry, that's my kid in the background there.
Right here. Put the pencil right.
All right, sorry, I'm being instructed to mute myself. All right, yeah, sorry, I've got 2 daughters. One is 7 and the other is 4. They're gonna head out for dinner here. So, all right. Okay. Anyway, we're talking about the binomial distribution. And what was I saying? Oh yes, is this probability distribution for a special kind of random variable. And this is the situation in which we apply the binomial distribution. So what we have to do is we repeat the same random trial n times. Okay, we're going to repeat the same random trial n times. And every time we do something, every trial has only 2 outcomes, all right? In that either something happens or it doesn't, okay? So it could be you flip a coin and we could say either it lands heads or it doesn't land heads, okay? If you want to do something like rolling a die, you've got to turn the outcome into something, either something happens or it doesn't. So you can say either we rolled the number 6 or we didn't roll the 6, okay? Or we rolled an even number or we didn't roll an even number. It has to be something either it did happen or it didn't happen. Now, these are traditionally labeled as success, meaning the thing happened, versus failure, as in the thing didn't happen. But they may not, the outcome may not necessarily be like a good thing or a bad thing, right? We could say either the part broke or it didn't break, okay? And, the thing that happened, we often label the quote success, but that's not exactly something that we want to happen, okay? Every trial that we do has to be independent of the other trials. So the outcome of one thing should not influence any other outcome, right? So coin flips are independent. Every time I flip a coin, what happens on the next coin flip, it is not dependent or is not affected by what happened in previous coin flips, okay? The next time I roll the die, what happens next is not affected by what happened in previous die rolls, okay? Every trial that we do has to have the same probability of success. So I can't take one die that has 6 sides and then swap it out for another die that has 20 sides or something like that, right? I have to do the same thing over and over so that the probability of a success, say rolling a 6, is going to remain the same for every single trial. Okay, and the thing that we are recording is the number of successes, okay? The number of times the thing happened, all right? And that's going to be our variable x. So we are going to do, just a silly example here. We're going to pretend we've got some special coin here, and we're going to say, I don't know if such a coin even exists in the real world, but we're going to say the probability that this coin lands heads. What is this coin? This is like a dollar coin. I'm not sure what we're looking at. Okay, but we're going to say the probability that this coin lands heads is going to be 0.7, which means the probability that it doesn't land heads is going to be 0.3. And what I'm going to do is I'm going to flip the coin 4 times. And we're going to say the coin flips are independent of each other. And I'm going to ask, what's the probability I get heads exactly 1 time out of 4 flips? Now remember, the coin favors the heads. Okay, so we're going to see how this works. Okay, now this is a binomial situation, and there is a binomial formula that we're going to use, but we're going to kind of work our way up to it by using kind of the classical rules of probability. So what we're going to do is we're going to list off all the possible ways we can get this situation where we get heads exactly 1 time in 4 flips. Okay, and that's going to be heads, tails, 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 heads, tails, 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 heads, tails, and tails, 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 heads. Okay, and those are the 4 outcomes, and there's no other way to get flip the coin 4 times and there to be heads exactly 1 time. And if you look at any one of these sequences and you say, well, what is the probability of getting this exact sequence? This sequence, we would do heads, which is probability 0.7, times tails, 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 which is going to be 0.3 raised to the 3rd power. If we look at this one and we say, all right, what's the probability of getting this exact sequence? We would do 0.3 for the tails times 0.7 times 0.3 times 0.3, and that also will be 0.7 times 0.3 cubed. Okay, so we can kind of, when we multiply all of these things, the probability of any one of these sequences will consist of 0.7 once and 0.3 3 times. So all of these things will be 0.7 times 0.3 to the 3rd. And there are 4 total possible arrangements. So I can take this number, 0.0189, and I'll raise it to the 4th power, or not raise it to the 4th power, but I'll multiply it by 4 because I've got 4 possible arrangements. So 4 times 0.0189 is going to be 0.0756. Okay. And I hope that's okay. I hope that makes sense as far as getting the total probability of getting heads exactly 1 time in 4 flips. Okay. So what if we extend this a little bit and we say, all right, let's flip the coin 4 times, and this time we want to see what's the probability I get heads exactly 2 times out of 4 flips. All right, and so once again, we're going to list off every single possible way to get 2 heads out of 4 flips. And there are 6 possible arrangements. They go heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, and tails, tails, heads, heads. Right, and you can try to think of another way, but this is it. Okay, that's every single possible arrangement for getting 2 heads out of 4 flips. And so once again, if we say, well, what is the probability of getting this exact sequence of heads, heads, tails, tails? Well, we have to get heads 2 times, which would be 0.7 times 0.7, and tails 2 times, which would be 0.3 times 0.3. And so that exact sequence of heads, heads, tails, tails is going to be 0.7 squared times 0.3 squared, or 0.0441. Okay, and then if we look at any one of these other arrangements, they're all going to be 0.7 squared times 0.3 squared. And therefore, the total probability of any one of these 6 possibilities happening is going to be 6 times 0.7 squared times 0.3 squared. Okay, and so the total probability of any one of these arrangements is going to be 0.2646. All right, so I just want to kind of pause here and just check in with you guys, and if it feels good, give me a thumbs up or a nod your head or something. And if you've got questions, let me know in the chat. Okay, all right, got a lot of thumbs up there, so thank you. Great. Okay, so if we want to generalize this, we can say, all right, all we have to do is we take the probability of success and we're going to raise it to how many times we need a success, right? And then we're going to multiply it times the probability of failure, in our case 0.3, and we're going to raise it to the number of times we need it, the failure to happen or us not to get heads, okay? And then that's going to be the probability of any one such sequence or any one such arrangement. And what we need to do is we need to figure out the number of arrangements. Okay, so we got the number of arrangement times the probability of a success raised to the number of successes times the probability of failure raised to the number of failures. Okay, if we looking at the same thing for the other one, we have 0.7 squared times 0.3 squared. We had 6 possible arrangements. So the total probability there, same pattern, number of arrangements times the probability of a success raised to the number of successes times the probability of a failure raised to the number of failures. All right, and so what is this number of arrangements, right? So what I did was I listed them out and I wrote heads, tails, 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 and heads, heads, tails, tails. And I wrote all of these things out and I said, you know, there's 4 possible arrangements for 1 head out of 4 flips, or there's 6 possible arrangements to get 2 heads out of 4 flips. And you don't actually have to go through and write every single possible combination down. There is a thing that we call the binomial coefficient, which tells us how many possible arrangements there are. And that's given by this kind of this tall parentheses where you write n over k, and this we read as n choose k, n choose k. The way we calculate this is n factorial, we divide by k factorial and n minus k quantity factorial, right? And so if you're not familiar with the factorial function, it's you're going to take the product of basically all of the whole numbers less than or equal to n. So 4 factorial is 24 because you're doing 4 times 3 times 2 times 1. 5 factorial would be 120. It's 5 times 4 times 3 times 2 times 1. And you know, these factorial numbers, they get really big really fast just because you're multiplying all of these numbers together. So anyway, if we did something like 4 choose 2, we have n choose k. So we write 4 factorial divided by 2 factorial times 4 minus 2, which is also 2 factorial. 2 factorial is 2, 4 factorial is 24, and we do 24 divided by 2 times 2, which will give me 6. Okay. If we had 10 trials and we want to see how many arrangements are there to get 4 successes, we would have 10 choose 4. So we would write n choose k, 10 factorial divided by 4 factorial times 10 minus 4, 6 factorial. So 10 factorial is this, 4 factorial is this, 6 factorial is this. And so you have, you know, all of these numbers, it gets quite big. 10 factorial is, you know, 3.6 million. And it becomes 210. Okay. Now, you don't have to do this. On your calculator, you might have a factorial function. Let me see if I can pull up my on-screen calculator. Okay, so on my calculator, I have an NCR button above the division sign. You might have a math button or a PRB button on your calculator. And if you hit the math or the PRB button, it might pull up a menu and you kind of like scroll around in your menu and you might see this thing that says NCR. And so the way it works on my calculator is I hit 10 and I'm going to hit shift divide, and that's going to give me C. It might show up as NCR on yours. And if I do 10 choose 4 and I hit equal, it tells me 210. Okay. And on your calculator, again, you might have to work through the menu to find NCR. In a pinch, you can always go to Google and you can do 10 choose 4. Okay, and if you do 10 choose 4 into Google, you'll get 210. So that's another thing you can do. In R, you can zoom in a little bit. You can do choose 10, 4, and that will give you 210. And then also on CCLE, there are reference tables. And in the reference tables, your first one is the binomial coefficients, and you can go n is 10 and choose, they have it choose j. 10 choose 4 is 210. Okay, right there. And so there's lots of ways to get these binomial coefficients. You know, you can do 4 choose 2 is 6 and things like that. Yeah, so if you have the TI-84, you're going to hit math, go through the menus, probability, and you're going to hit choose option 3 for NCR. And the way you would have to enter it into your calculators, you would enter the 10 first, go through the menu, pick the NCR, and then you would enter the 4, and then you would hit enter. And that should give you your 10 choose 4, okay? If you have any questions about how to use your particular calculator or something like that, I'll stick around in office hours. I've probably seen most people's types of calculators, and I can probably help you navigate through that. So if you got questions about how to use it in office hours, that's an option, okay? And again, you know, your quizzes and exams are open book, so you can always use the reference tables as well, okay? So these reference tables are available under week 2, and you'll use these reference tables throughout the rest of our course. So you'll want to save these, okay? So they're also available in the reference tables. All right, so anyway, we'll go through it and we can say, all right, when we found the answer, we got this, and again, we can do this by using the binomial formula, number of arrangements, 6, n choose x, which is 4 choose 2, probability of success as far as flipping the coin, 0.7 probability of getting heads, 0.7 squared, probability of getting tails, 0.3 raised to the number of tails we want, 0.3 squared, and that's going to give us 0.2646. Okay, so we have n choose x, p to the x, 1 minus p to the n minus x. And so let me just kind of show you. In R, we could type this out. I can do choose 10 comma 4. I can do 0.7 raised to the second power times 0.3 raised to the second power. And that is wrong. What did I do? Oh, not choose 10 4. No, it's 4 choose 2. Okay, and that gives me the answer that I'm looking for, 0.2646. Okay. Now there's already a binomial probability calculator in R, and it's D binom, D for kind of what's known as a density, but D binom for the this particular outcome. And what we want is we want to get 2 as our number of successes. We have 4 trials, and the probability of a success on any one trial is 0.7. So I'm going to do 2 comma 4 comma 0.7, and that also gives me the exact same number of 0.2646. Or you can do this as well. On the calculator, 6, 10 choose 4 times 0.7, 0.7 squared times 0.3 squared. And all of these things will give me, I'm doing the same thing again. Not 10 choose 4, I want 4 choose 2. Okay, 4 choose 2, 0.7 squared times 0.3 squared, 0.2646. Okay, so I've basically done the same calculation like several different ways here, all to show that this is the formula that we're using. Okay, all right, so let's try an example here. And okay, so I'm a fan of basketball, and so I'm a big Lakers fan, but I have great respect for the other teams, and Steph Curry plays for the Golden State Warriors, and when he is healthy and doing well, he is perhaps one of the best shooters in the league, and possibly of all time. And as far as his free throw percentage, it is very high at 92.6%. And so we're going to, we're making several assumptions here, but we're going to assume that the probability he successfully makes a free throw for any one given shot is going to be 0.926, okay? And depending on the game, he might have several opportunities to make a free throw, or he might not. We'll just arbitrarily pick the number 5, okay? And so here's the question. What's the probability he misses one free throw, exactly one free throw, if he takes 5 free throws in the game, okay? And so why don't I give you guys a minute to figure this out, all right? You can use your calculator, you can use R, you can try writing it out. I'll go ahead and just pause the recording. And if you're following along in the video, why don't you pause the recording here as well? And we'll go over the answer once we resume. All right, so we'll go over the answer here. Okay, so when it talks about, here, I will pull up I'm going to just go over the answer right here. And so here we've got n equal to 5. We got 5 free throws. And then we have P, the probability of making a free throw, to be 0.926, right? And so what is our X? X is, so the question says probability of missing 1. Okay, probability of missing 1. Okay, so probability of missing 1 is the same thing as probability of making 4. Do we feel that that's okay? So I'm going to do n is equal to 4, or x is equal to 4. And so I will have 5 choose 4, 0.926 raised to the 4th power times 1 minus the probability of not making it is probability of making is 0.926, and then missing will be 1 minus 0.926. So that's what, 0.074. That has to happen one time. Okay. So here, when I do this, what is this going to be? So 5 choose 4 is just 5, but I'll go ahead and I will do this. 5 choose 4 times 0.926 raised to the 4th power times 1 minus 0.926, which is just 0.074. We're going to raise that to the 1 power. I'm not going to bother doing that. And so I get 0.272. 27205, I guess. Okay. I have this written out here. N is 5, P is 0.926, X is 4. We could also use R to do D binom, 4 choose 5, 0.926. Okay. This would also be, if you wanted to kind of flip the question around, and you could call P being, the number of the probability of missing being 0.074, and you could do like a 5 choose. So I could do D binom 4 choose 5 with the probability of making it being 0.926. If you wanted to say what's the probability of missing 1, then we say 1 out of 5, and then the probability of missing any one basket is going to be 0.074. And this is also giving me the same answer of 0.2720481. Okay. Do we feel good about that? Okay. In the interest of time, I will just skip over this and I'll let you guys do this on your own time. So it says, if the admission rate at a university is 16% and 100 people apply, we're going to just say this is completely random. And again, these are perhaps not good assumptions to be making, but this is what we'll say. Okay, the answers are there. And the mean and standard deviation of a binomial distribution, you could go through and make the entire table and go through the entire process that we did last week, where you say, the mean or the expected value is mu times the probability is x times the probability that x equals x, and so on and so forth, and do that for every single thing. But there's just a convenient shortcut. Convenient shortcut. We could say the mean is n times p, and I think that makes sense. That if you try something n times, you got n trials, and the probability of success on any one of those trials is p, then the overall expected number of successes that you would expect is going to be n times p. Okay, and the standard deviation is given by this. We won't get into the derivation of this thing, but we'll just say this is something that you need to know. Okay. All right. Okay, so we're going to keep moving on here. And now let's discuss the normal distribution. Okay. So the normal distribution is probably one of the most important distributions that we will encounter. And we have distributions based off of the normal distribution, such as the t distribution, which we will see shortly, and the chi-squared distribution, and also the f distribution. So a lot of things derive from the normal distribution, also known as the Gaussian distribution. it is a continuous distribution in contrast to the binomial distribution. The binomial distribution, I didn't really talk about this, but it's a discrete distribution. You won't get any decimal values in a binomial distribution. You're either going to get it, because the question is how many successes, right? What's the probability of Steph Curry making 3 shots, 4 shots, 5 shots? Okay, and there's never going to be an outcome where you get 3.2 successes or 3.55 successes. It's just going to be a whole number of successes. Whereas with the normal distribution, it's a continuous distribution, meaning you can get decimal values. And overall, the distribution is unimodal and symmetric. It is centered at the mean, and the most common values are at the mean. And that's represented by this graph where the peak, the line is tallest in the center in the mean, and lines far away from the center, the line gets lower and closer to 0 as you move farther away from the center. So values near the center or values near average show up frequently. Values that are greater than average are show up less frequently, and values less than average also show up less frequently. And as you get much greater than average or much lower than average, those show up much less frequently. Okay. And one rule of all probability distributions is that the total area, because this represents kind of the total probability of all possible outcomes, that total area has to equal 1. Okay. Just because probability equal 1 means something in here is possible. And that's what we have here. Okay, so this is, you have this thing that looks like a hill, and the total area underneath this hill, underneath the curve, is equal to 1, right? So if some of you have taken calculus, a lot of you have taken calculus, some of you haven't, but don't worry. If you've taken calculus, the integral is the area under the curve. So the integral of the entire distribution is going to be equal to 1. Good. Okay, we'll start off with what's known as the standard normal distribution. This is also called the Z distribution, or because it's related to Z-scores, which we'll get in a moment here. And this is a normal distribution where the mean is 0 and the standard deviation is equal to 1. And this is actually a picture of a standard normal distribution. The mean is 0, it's at the center is 0. And standard deviation 1 looks pretty much like this, where, by the time you're out at 3 and -3, your values are very close to 0. And, at 4 and -4, it's pretty much 0 there, okay? So because it's a continuous distribution, this is a little bit of a strange concept, the probability of getting any one exact value. And so we're thinking like an exact value where there you have an infinitely number of decimal places, and it's precise to an infinite number of decimal places. The probability of getting any one exact value is 0. Okay, so just kind of an example here is human height would be a continuous distribution, and it's often modeled with a normal distribution. Now, if I asked you, how tall are you? You might say, I'm 5'4", 5'4" inches. But the truth is you are not exactly 5'4". You're not exactly 64 inches. If we had a measuring device with infinite precision, you might be 64.02511789916, whatever, however many decimal places. If we had this, infinitely accurate measuring device, okay? And the probability that anybody is exactly 64 inches with infinitely many zeros, 64.0000 with infinitely many zeros, the probability of being exactly that amount, that probability is 0, okay? It's a little bit strange. And we're just accustomed to kind of rounding everything off in life. And so you're under the false impression that we have kind of these exact amounts, but we really don't, right? So anyway, I'm going off on these tangents here. if we just kind of say, what's the probability that z is less than 0, right? So here's kind of our picture. And if I say, you know what, let's draw a vertical line, right? So the probability that z is less than 0, I would express mathematically writing this. What's the probability that z is less than 0? I would express this mathematically like this, and I would draw a picture, and I would draw a vertical line at 0. Here's my curve. And I would say, all right, let's just shade in everything to the left of 0, right? How much area is to the left of 0? And if you know that the total area is 1, I think the answer is very easy to see that the area to the left is 0.5, okay? 0.5. And so the flip side is, I'm sorry, these examples are maybe too simple here, but if we just said, all right, well, let's flip this around. What's the probability that z is greater than or equal to 0? Then the answer is also going to be 0.5. Okay. Oh, all right. So how did we get 0.5 here? So the answer is, you know, if we have, this is kind of my picture. And the total area, if we shade everything in, the total area is equal to 1, right? And what I'm doing is I'm saying, you know what, I'm going to draw a vertical line right in the middle, okay? Right in the middle. This is z equal to 0, and we're going to shade everything to the left here. Where's my paint bucket? Okay. So let's go ahead and shade everything to the left here, okay? And so the question is, how much have I shaded? What is the area? What is this shaded area? Okay. Well, the total area under of the hill of the curve is equal to 1, and I think we can see that this is half of that, right? So the shaded area here is going to be 0.5, right? And then what would be the unshaded area? The unshaded area is also going to be 0.5, right? I can just say, well, everything has to add up to 0.5. So I'm going to just do 1 minus the shaded area. I get 1 minus 0.5, which is also 0.5. Does that answer your question? I hope that's okay, right? So we just started off with kind of this rule, this premise that said everything, the total area is going to equal 1. Okay. All right, and so that's what we have here. We've got the probability of z being less than or equal to 0, or less than 0 is 0.5. The probability of z being greater than or equal to 0 is also going to be 0.5. Okay. So this is how we can write. Probability that z is greater than or equal to 0 mathematically is going to be 1 minus the probability that z is less than 0. This is also 0.5. All right, there's something called the empirical rule. This is also known as the 68, 95, 99, 7 rule, just because these are the numbers that show up. But this says approximately, if you draw this standard normal distribution, and you mark off kind of barriers where the z-scores go from 1 to -1, from 2 to -2, and 3 to -3, you're going to get these proportions. So approximately 68% of the data will have z-scores between 1 and -1, or mathematically we write probability that -1 is less than z less than 1 is approximately 0.68. Around 95% are between 2 and -2. And almost all, 99.7%, are between 3 and -3. So we're going to write around 0.997. Okay, and so my picture looks something like this. And I'm not going to be able to replicate this, or I don't know, maybe I can. The idea being, if I were to, what am I doing here? Okay, please work. I hope this works. Okay. So the idea being, if I were to shade this region here. Okay, yes. So this is from z equal to -1. Oh, that's not what I want. Go away. From -1 to 1, if I shade this, again, the total area is 1. This is about 68%. Okay. And if I go from -2 to 2, so let me just pick another color here. I don't know what a better color would be, but we'll go from here. Oh, that's not right. This one. Okay, so we'll go from here to here. These colors are visible for you guys. Okay, so from here to here, we're getting most of our stuff. That's about 95%. Okay, and then if I say, you know what, let's keep going. All right, and we're going to shade in this. This is almost everything. This is almost everything, not quite everything, but this this covers 99.7%. So almost everything is shaded, okay? And you just have this tiny, tiny little sliver over here, this tiny, tiny little sliver over there. That's the difference between 99.7% and 100%, okay? And technically, it goes on to negative infinity and positive infinity. It's asymptotic as it goes out. It's just so close to zero that, you know, it's hard for us to even represent in the picture. Okay, but this is the idea here. Okay, 68, 95, 99.7. Those are good numbers to remember, especially this 95 and the 2, right? So you kind of hear this 95% and z-scores of 2 or -2. I would say that's especially good. Okay, so just kind of using this as a guide. And I said, what is the, what proportion of z, what is the proportion where z has an area greater than 1? So it's, I guess just kind of drawing this picture here. So z greater than 1 is, so here's z1, and let's just shade in. Z greater than 1 would be here, here, and also, can I get that tiny little sliver? Yeah. So how much have I shaded in here? Approximately. Approximately, how much have I shaded in here? What do you guys think? Yeah, okay, all right. So we got, so Allison says around 16%. And yes, I would agree, okay? Because the idea being that based on the empirical rule, we have around 68% here, which means in total, right? So kind of the two sides would equal around 32%. And we would expect this to be around 16% and this side to be around 16%. Okay, so if I were to shade something like this over here. Okay, so we'd have around 16% over there, 16% over there, 68% in the middle. That's what we have. Okay, is everyone else okay with that? So, all right. So that's what we got. All right, now if we go on and we say, all right, let's try something, something that's not like a whole number, like 1, 2, or 3. Okay, and this time I'm going to say, well, what proportion of z? What proportion has z less than a 0.42? Okay, what proportion of z? What's the probability that z is less than 0.42? Okay, well, this we can no longer use the empirical rule to kind of answer. We cannot rely on the empirical rule here. What we have to do is we got to use a reference table. Okay, and so you know, open up this reference table here, and you're going to go to areas under the normal curve. And here, this is always area to the left of a z. So z starts off it kind of starts off at -3.4. And it says, if you go to z equal to -3.4, the area to the left of -3.40040 is 0.0003. Okay, so this first picture this is basically saying, you know, if you if you go to, if you draw a line at negative 3.40, okay, something like this, and you were to shade this little piece, this tiny little sliver over here, the amount shaded, this area, is equal to 0.0003, okay? And as you get closer, so if you go to negative 3.0, okay, and then we shade everything to the left of negative 3.0. So this, oops. Okay, that little piece right there, everything to the left of negative 3.0 would be 0.0013, okay? 0.0013. Now, what we're asking is what proportion has z less than 0.42? Okay, so here I'm going to draw a line between 0 and 1. This is, I'm just eyeballing this, but let's 0.42. I'm going to just draw a line right there. Okay, we're going to just pretend this is z equal to 0.42, and I'm going to shade everything. I'm going to shade everything to the left. 0.42. Okay, so I'm going to say, how much am I shading? How much area is this? Okay. That's the shaded area. All right. So the answer to this comes from our reference table. Okay. And so this is our picture, 0.42. We're shading everything to the left. We know the answer has to be more than 0.5. And what we're going to do is we're going to go to our reference table. We're going to go to the second page of table 3. Table 3 is areas under the normal curve. There's 2 pages to it. And we're going to go to the row z equal to 0.4 and the column 0.02. Okay, 0.4, z is 0.4. The column is going to be 0.02, and that kind of gives us our answer, or our value z equal to 0.42. And it says this area is 0.6628. Right? So this area is going to be 0.6628. So we go 0.4, 0.02, 0.6628. This table looks a little bit different. So why do we go to column 0.02? And that's, well, so we have z equal to 0.42, all right? And the way the table is arranged is you go up, the 10th place is in the rows, and then the column, the 100th place is in the column, okay? Because they could have done one table where it was like 0.00, 0.01, 0.02, 0.03, 0.04, 0.05. But what they did was, rather than having just one string of values, 0.01, 0.02, 0.03, you know, 0.40, 0.40, 0.41, 0.42, 0.43, what they've done is they've kind of rearranged this in a grid, okay? So you go to the row 0.4 for the 10th place, and then the 100th place is in the column 0.02, okay? So I hope that answers that. The table always only gives you the area to the left. You will only get the areas to the left from the table. So at z, you know, 0, 0, you get 0.5. And as you get farther and farther away, you know, the area to the left gets closer and closer to 1, you know, 0.9998, things like that, okay? At 0.42, the area to the left is 0.6628. The table always gives you only the area to the left. Okay, we can also use R, and there's a tool in R called p-norm. So we want the values from the normal distribution, and we're going to type in z equal to 0.42, p-norm, 0.042, and the values from R are a little bit more precise. Our tables give us 4 decimal places of precision. R gives you even more, and this gives us 0.6627573, which rounds off to 0.6628. Okay. Now, Yeah, so can it ask us about greater than 0.242? Yes, that would be the next question, right? So if we want the area to the right, what's the probability of being greater than 0.42? You take that number and you subtract from 1. So if we ask this question, what's the probability z is greater than 0.42? We would just take the area to the left and do 1 minus that, okay? So the answer to what is the area to the right, okay? Like if I took a different color here, and I said, you know, let's shade this side in blue or something like this, right? I say, all right, how much is over here? What is this area? This area is going to be, whoops, 1 minus 0.6628, and I get 0.3372. Okay. And there you go. So the area, you know, what's P being greater than 0.42 would be 1 minus the probability of being less than 0.42. Okay. So far, so good. All right, let me go ahead and give you your next view quiz answer. The second view quiz answer for today is the letter C. The letter C as in cat. C as in cat is your second view quiz answer for today. C as in cat. All right, so why don't you guys take a minute here and use your reference tables and get the answers to these questions here. Okay, I'll go ahead and I'll pause the recording. All right, so let's go ahead and go over our answers. So here we just asked, what is the probability? So we're going to go to z is less than negative 1.4. So I'm just kind of arbitrarily, that's not quite right, but something like that. And so if we shade in everything to the left there, something like that, we're going to just go to their table here. Let's pull this up. We're going to go z equal to negative 1.4. So it's negative 1.40, and we're going to find 0.0808 for that answer. Oh, I keep making this mistake. All right, so the probability that z is less than negative 1.4, 0.0808. Okay. All right. If we do negative 1.04, okay, for this one, I've got to come over to the row negative 1.0, and I go to the column 0.04, and I get 0.1492, 0.1492. And so that picture, negative 1.04, I don't know, something around there. And we'll just shade it in a little bit of it. Maybe we'll pick a slightly darker shade here. Okay. And so everything to the left there, 0.1492, everything to the left, something around there, 0.1492. If we did greater than 1.04, okay, so I would draw a vertical line like right here, and I would shade everything to the right. Let's pick okay, so everything over here. All right, and how much is that? Okay, well, we would take, okay, so we could look up positive 1.04. Positive 1.04 gives me 0.8508. Okay. So the area to the left this way is 0.8508, which means this is going to be 1 minus 0.8508. And that is also 0.1492. Okay, I hope that's all right. So, so if you did this with R and just got the answers, you get, if you p norm negative 1.4, you get 0.0808. Negative 1.04, you get 0.14171492. Positive 1.04, 1 minus the area to the right of positive 1.04 is also going to be 0.1492, 0.14917. Okay, and these are kind of pictures that I've drawn. Area to the left of negative 1.04, row is negative 1.4, column 0.000808. And we get this. And we get this, okay, 0.1492. Okay, any questions on this? Do we feel okay about all of this? And so one identity that could be useful is that the area to the right of Z is equal to the area to the left of negative Z, right? So when we said, what is the area to the right of 1.04? That area is equal to the left of negative 1.04, right? So when you looked at what's the area to the left of negative 1.04, you got 0.1492. And when we ask kind of basically the same question where we say, what's the area to the right of positive 1.04, basically these images are mirror images of each other, right? Here we're looking for the area to the left of negative 1.04. Here we're looking for the area to the right of positive 1.04. So you could see, I think, if you flip the mirror around, you can see that this is the same area. And so we're going to get the same answer, 0.1492. Okay. So if you're comfortable with that, you can use that as a shortcut. If you're not so comfortable about that, you don't have to. You can always use the table and say, the table always gives us the area to the left. And if I want the area to the right, I'm going to do 1 minus the area to the left. And that's always going to work as well. Okay, any questions about any of this? All right, so what we want to do is we want to generalize the normal distribution, the standard normal distribution, to other normal distributions where we might not necessarily have a mean of 0 and a standard deviation of 1. Okay, so for example, if we look at the height of adult men in the United States, and these are just approximate numbers, the exact numbers that have more decimals of precision and gets a little bit more messy, but just for simplicity, we'll use these numbers here. Okay, we're going to say the mean height for men in the United States is 69.5 inches. Okay, and we've got a standard deviation of around 3 inches. Okay, for adults in the United States. And so we're going to ask a question, what proportion of adult men in the US are shorter than 72 inches? So that's 6 feet tall. So what proportion are shorter than 72? So our picture would look like this. In the center, we put in 69.5, and I'm going to just draw a cutoff line at 72, and we want to know what's the area to the left of 72. Okay, so what we're going to do is we're going to convert this height, 72, and we have to turn it into basically a z-score. Okay, a z-score is the distance we are from the mean, but expressed in standard deviations. Okay, so a z-score is our distance from the mean, but expressed in standard deviations. So let me just go back and copy this picture. So our mean is 69.5, and here our cutoff line is 72. And what we want to do is we want to figure out our z-score. So we're going to say, what's the distance from the mean? So we're going to do, we're going to just do value minus the mean. That's our distance from the mean. And then we're going to divide by standard deviations to say, what is that distance in standard deviations? So our distance from the mean, 72 minus 69.5, that's a distance of 2.5. How many standard deviations is 2.5 inches? Okay, well, each standard deviation is 3 inches. So 2.5 is just a little bit less than 1 full standard deviation. So we're a little bit less than 1 full standard deviation above the mean. Okay, so 2.5 divided by 3 gives me 0.8333. All right, and I'm going to just round to, z equal to 0.83. Okay, so we're about 5/6 of a standard deviation above the mean. A little bit less than 1 full standard deviation above the mean. 1 full standard deviation above the mean would be 72.5 inches, but we're at 72, so we're going to say we are a little bit less than that. Okay, so here we're going to go. So the probability of having a height less than 72 is equivalent to the probability of having a z-score less than 0.83. Okay, so to convert to a z-score, we're going to take whatever value we have, we're going to find its distance from the mean, x minus the mean, and then we're going to divide by the standard deviation. So our z-score is going to be 72 minus 69.5 divided by the standard deviation 3. We get a z-score of 0.83. And now at this point, now that I have a z-score, I just go to the table, right? I just go to the z table. I'm going to look up z equal to 0.83. 0.83, I go to the row 0.8, the column 0.3, and I get 0.7967. 0.7967. And that's going to be my answer. So in my picture here, if I shade in everything to the left here, this area is 0.7967. So just under 80%. Okay, around 80% of adult men in the United States are under 6 feet tall, according to these made-up statistics that I have. All right, is that okay? Process there. All right, great. So why don't you guys try this one out? Okay, what proportion of adult men in the US are shorter than 71 inches? So go ahead and take a minute to solve for this one. I'll go ahead and pause the recording. All right, so we'll just do the thing real quick. Okay, so again, our z-score is our value minus the mean divided by our standard deviation. So we have we're asking 71 inches. Our mean is 69.5. We divide by a standard deviation of 3. So 71 is only 1.5 inches above the mean. Each standard deviation is 3 inches. So this is 1/2 of a standard deviation above the mean. And so if we draw our picture, you know, in the middle we have 69.5, and here we're going to 71. We're 1/2 a standard deviation above the mean. So I'm going to just look for probability that z is less than 0.5. Where's my z table? Here it is. So we're just going to get 0.6915. Z is equal to 0.50, 0.6915. And that's going to be our answer here. Right, so we got our z-score is 0.5. The probability that z is less than 0.5 is 0.6915, and this is our picture. So just under 70%, it's around 69%. Okay, great. Okay, and all right, so if we do one more, I'll just go ahead and give you the answers for this one. So what is the probability that a randomly chosen adult male has a height between 71 and 72 inches, so between 5'11" and 6 feet tall? What's the probability that someone falls in that zone? Okay, well, the way we're going to do this is, you know, we first have to find the area to the left of 72, which we've done. We're going to find the area to the left of 71, which we've done, and we're going to take the difference between these things. Okay, so from the previous slides, we have the area to the left of 72 to be just under 80%, 79.7967. The area to the left of 71 inches to be 0.6915. And so the difference between these two is 0.1052, and that's going to be our answer. I think this question is a little bit better with an illustration. Okay, and the idea here is, here's my picture. I've got 69.5 in the middle, and I'm drawing kind of two cutoff lines, one cutoff line at 71 and one cutoff line at 72. And what we want to know is what's the area between 71 and 72. And so the way we're going to do this is we're going to take the area to the left of 72, which we found again earlier on a previous slide to be 0.7967. We're going to take the area to the left of 71, which again from our work in a previous slide is 0.6915. And we say, all right, this big area minus this area is going to be left, is going to leave us with this slice right here, the slice between 71 and 72. And so if I take the difference between 0.7967 and 0.6915, I get the area in between, which is about 10.5%, a little something around there, between 10 and 11%. of adult males in the United States have heights between 71 and 72 inches. Okay, again, using my fake numbers that I'm using. All right. I hope that's okay with you guys. Yeah. All right, so sometimes we will have a situation where we have to kind of work backwards, right? So we might give you something like a percentile, and we'll ask you, what is the height associated with this percentile, or what is the value associated with this percentile, right? And so, let's say you're trying to sell a hat or something, and you want to make sure that, the hat accommodates, say, 96% of people's heads. So, if you adjust it from the widest to kind of the narrowest levels of the thing, what is it going to do, right? So you want to accommodate the middle 96%, right? So we're going to just say, 4% of people who have heads that are a little bit too big or heads that are a little bit too small, they're going to have to shop for a different sized hat. If we want to get the middle 96%, then we're going to say, all right, the max size will be the 98th percentile, and the smallest size will be the 2nd percentile. Right? So if we go from the 2nd to the 98th percentile, that's going to cover the middle 96%. We're going to miss the top 2% of people with really big heads and the bottom 2% of people who have, small head circumferences and things like that. All right, and again, I'm making up some numbers here, but just for simplicity, let's say the mean head circumference is 23 inches and the standard deviation is 0.8 inches. I don't know what it really is, but so don't fact check me here. But let's say these are the numbers, and we're going to ask, okay, well, what's the biggest size we have to make for our hat, right? So what's the 98th percentile for head circumference? Okay, so we've got the mean is equal to 23. The standard deviation is 0.8. And what we want to know is, if we were to draw a picture, the picture looks like this, all right? There's some number here such that when I shade in the area over here, okay, this area equals to 0.98. That's what we're saying, okay? This is the 98th percentile. All right, and so we want to know what is this number here? Okay, what is this number? Okay, well, first let's figure out what is the Z that goes with the 98th percentile? Okay, and so what we're going to do is we're going to go to our Z table, okay? And this is very important. Do not look up Z equal to 0.98, okay? So what is Z for 98th percentile? And this is important. Do not find Z equal to 0.98, okay? This is wrong, okay? What you want to do is find the Z. So the area to the left is...
From your calendar, I exam at Granada Hills Optometry.
Okay.
Starts in 10 minutes.
All right, well, that's my wife's appointment there. Okay.
From your calendar,
thank you, Alexa.
I exam at Granada Hills Optometry. Starts in 10 minutes.
All right. I'll have to remember to mute this device as I'm glad it was an eye exam and not something more embarrassing or something like that. But okay. Find the Z so that the area gives us something around 98%. Okay. All right. So we have to look through all of the numbers here, and we want to find the number that gives us something as close to 98% as possible. All right. And, you got to search through all of them. Luckily, they're all in order, so it's not too bad. And I see two candidates. I got 0.9798. That's pretty close to 98%. And I got 0.9803. Okay. Now, this is students make a lot of I don't want to say a lot of mistakes, but this is a common place where students make mistakes, is that I don't know, for whatever reason, as students search through these things, they'll go, oh, 0.979383, that's close enough to 98%. But really, you got to search for the best answer, okay? And that's going to be either this one or this one, and the one that's closest. You don't have to interpolate numbers or anything, but we'll just say, okay, the best number is going to be 2.05, because that gives me 0.9798. Okay, if because that's 2 10,000ths away, and this one's 3 10,000ths away. So we're going to say z is equal to 2.05. Okay, so we'll use z equal to 2.05. This gives area equal to 0.9798. All right. Is that okay as far as identifying that z-score? Finding the one that corresponds to 98% being 0.9798. Okay, all right. Thank you for your thumbs up there. Okay, so now once we have this z-score, 0.97, z-score being 2.05, corresponding to the area, 0.9798, now I have to convert this from a z-score back into x. Okay, so I'm going to go ahead and just kind of make a new slide here. And so we have z equal to 2.05, and we have the formula. Z is equal to basically x minus the mean, our value minus the mean divided by our standard deviation. So I'm going to plug in the values I have, 2.05. I don't know my x. That's what I'm looking for. My mean is 69.5. My mean is 23, and my standard deviation is 0.8. Okay, so now it's just a matter of solving for x. So I'm going to go 2.05 times 0.8. What is that? Something, okay? Is equal to x minus 23. I add 23, so I'm going to get x is equal to 23 plus 5 times 1.64. Okay, so I get 24.64 is equal to x. Okay, so I think I wrote all of that down here. What is z-score? That gives us 0.98 to the left. We search the table and we get 2.05, and then we plug that in. X is 24.64. 24.64. Okay. All right, so let me give you guys an example for you guys to work through. And I know, and the problem I said, the middle 96%, but if we did the negative second, or just the second percentile, it would be a boring problem just because you get pretty much the same value. The z that corresponds to the 98th percentile is basically the negative of the z that corresponds to the second percentile. So just to make it a little bit interesting, why don't you guys find the head circumference that corresponds to the third percentile? Okay, and I'll go ahead and give you guys another minute here to work on that. And when you find your answer, go ahead and give me a thumbs up here. All right, so what is a head circumference that corresponds to the third percentile? So what we're going to do, like before, is we're going to start with our table, and we've got to find the z that gives me the third percentile. So we're looking for the z that gives me an area to the left of 0.03, right? So just kind of my little picture here. Draw a picture. So this time we want to know, okay, this area here is 0.03. Okay, what is the z that does this? And then we want to convert that to the x. Okay, so I'm going to go to the table. We're going to look for an area 0.03. All right, so we're looking through here. I got 0.0287, 0.0294, 0301. So that's, I think this is our best candidate. Negative 1.88, z equal to negative 1.08. Negative 1.88 gives me an area of 0.0301. All right, so we're going to say z is equal to negative 1.88. And then we say, all right, z is equal to x minus the mean divided by the standard deviation. So I get negative 1.88 is equal to x minus the mean of 23 and the standard deviation of 0.8. So 23 minus 1.88 times 0.8 is equal to x. What is that? Minus 1.88. 22.8496. So pretty much 22.85. But if we kept all of our decimal values, we get this 22.8496. That's the, oh, what did I do? Did I mess something up? 23 minus, oh, I typed in 0.08. That's okay. All right, 21.496. That's better. Sorry, 21. So don't make silly mistakes like I did, and make sure your decimal places are in the correct spots. All right, 21.496 is our answer. 23 minus 1.88 times 0.8. Okay. All right. It's hard for me to read the room just because we're in Zoom, and a lot of you guys are giving me thumbs up, but out of 61, I'd say maybe like 20 of you or so are giving me thumbs up, and I appreciate all of you who are giving me thumbs up. That does leave just kind of a mystery question for like the other 40 of you, and you guys aren't saying anything, so I'm just hoping everything's okay. I do appreciate all of you who are giving me thumbs up, or those of you who have your cameras on and you're smiling and nodding along. That gives me confidence, and I just hope everyone else is also doing okay. So yeah. All right, let's. I'm going to just take a jump in the textbook. So chapter 4 is all about the normal distribution, but we're going to take a leap in the textbook and jump ahead to section 5.4, and then on Thursday's lecture, I'll cover kind of the rest of chapter 5, and we'll also get into chapter 6. So a little bit of hopping around here. I think that's okay. We're going to look at the normal approximation to the binomial distribution. Okay. And so earlier we talked about the binomial distribution, and then we just talked about the normal distribution. And so this section is all about, when you have a really big binomial distribution, like a really big sample size, the binomial distribution looks a lot like the normal distribution. Okay, and so what we mean is when we say sample size is large, it's going to depend on both n and p, right? So what probability we're talking about. So if n times p is greater than or equal to 10, and n times the quantity 1 minus p is also greater than or equal to 10, then we can approximate the binomial distribution with a normal distribution, which often makes our calculations easier if we're working stuff out by hand. Okay. And if that's the case, if we're going to approximate the binomial distribution with the normal distribution, then for the normal distribution, we're going to use the mean and standard deviation. And these are the same mean and standard deviation that defined our binomial distribution. So earlier today, back in one of the earlier slides, we said the mean of the binomial distribution is n times p. We're going to plug that in as the mean of our normal distribution. And we said the standard deviation of the binomial distribution is the square root of n times p times 1 minus p. We're going to plug that in as our standard deviation of our normal distribution. And if we do that, we can approximate the binomial distribution with a normal distribution. Okay, let me go ahead and give you your last view quiz answer for today's lecture. So week 2, Tuesday's third view quiz answer is the letter D. D as in dog. D as in dog is your last view quiz answer. D as in dog, last view quiz answer. Okay, so we'll do an example. And one thing that throws students off is this thing called continuity corrections, and you'll see it mentioned in the book. And basically, with the continuity correction, what we have to do is we have to add basically like 0.5 or minus 0.5 to our cutoff values, and it feels a little strange at first. But the reason why is because the normal distribution is continuous, whereas the binomial distribution is discrete. And anytime you're trying to approximate a discrete distribution with a continuous one, you get these weird situations. Okay. One thing to note, all right, is that this applies only, this continuity correction business only is applied in this exact scenario when we're trying to approximate the binomial distribution with the normal distribution. Sometimes students will get a little bit confused and they'll apply the continuity correction to just a regular normal distribution problem, or they'll apply the continuity correction to a regular binomial problem. And it just leads to kind of wrong answers. So I will show you what the continuity correction is, but it applies only to this situation where we are approximating the binomial distribution with the normal distribution. Okay, so please don't make one of these mistakes. I always feel bad having to take off points there. All right, so we're going to do plus or minus 5.5, and I'll show you what it is, right? So here's kind of a scenario where we would use this thing, where we would approximate a binomial distribution with a normal distribution, right? So it says I'm going to flip a fair coin 100 times. Flip a fair coin 100 times. And we want to know what's the probability that the coin is going to land heads 65 times or more, right? So this is a binomial problem. N is 100. P is equal to 0.5. And here we're asking X is equal to 65 or more, right? And so technically the exact answer, this is the reason why we want to do something like this. The exact answer would require a whole bunch of tedious calculations. We would have to do, so remember, binomial is n choose x, p to the x times 1 minus p to the n minus x. Okay, so I would have to do 100 choose 65, 0.5 to the 65, and 1 minus 0.5, which, luckily for us is also 0.5, and I would raise this to the 35. But then I would have to also say, because it says 65 or more, I would have to say, okay, what's the probability of getting 66 heads? 100 choose 66, 0.5 to the 66, 1 minus 0.5 to the 34, plus 100 choose 67, plus 100 choose 68, all the way up to 100 choose. So there's a whole bunch of these numbers to calculate. 100 choose 99 and 100 choose 100. Right. So I would have like 36 of these things to crunch out, multiply, and add up. And that's just painful. Okay, so we don't want to have to do that. So what we're going to do is we're going to approximate this. We're going to say, you know what? Because what it ends up looking like is that you end up having this normal binomial distribution with all of these kind of bars and stuff, and it ends up looking a lot like overall it ends up looking a lot like the normal distribution. Okay, and so here imagine having a bar centered at 65. Okay, and the next bar is centered at 66. This bar is centered at 64, and so on and so forth. And what we want to do is we want to get all of the bars, right? So there's more bars going in this direction, and there's more bars going in that direction, all the way up to 100, all the way down to 0. I've got a bar centered at 64. I've got a bar centered at 65. And we want to get everything 65 and higher. And so if I were to shade in the entire bar for 65 and, whoops. Shade in the entire bar for 65 and everything higher. Okay. My cutoff line for this bar is not exactly at 65, and it's not at 64 either. It's like halfway between 64 and 65. Can you guys see that as far as this bar? Okay, so my continuity correction says, you know what? don't draw a line at 65. If you draw a line at 65, you're like only getting half of the bar. Okay, so we're actually going to draw our cutoff line is at 64.5. It's not at 65, it's not at 64, it's in between. Okay. So what I'm going to do now is I'm going to do the normal approximation to the binomial. Okay. So we're going to say the normal approximation, is going to have mean n times p, which is going to be 100 times 0.5. So my mean is going to be 50. And my standard deviation is the square root of n times p times 1 minus p. So that's the square root of 100 times 0.5 times 0.5. So this ends up being 25. The square root of 25 is 5. So my normal distribution, the normal distribution that approximates the binomial here is going to have a mean of 50 and a standard deviation of 5. And my cutoff value is going to be at 64.5. Okay, so I'm drawing cutoff value at 64.5. And so I would do a normal distribution problem here. Okay, so I have z equal to 64.5. I subtract off the mean of 50 divided by the standard deviation of 5. And I get, what do I get? 2.9, a z-score of 2.9. And we ask, what's the probability that z is greater than 2.9? And that area is 0.0019, 0.0019. So if you flip a coin 100 times, we will, the probability of you getting 65 heads or more, it's not very high, it's 0.0019. Okay, so why is our cutoff value at 64.5? So let me see if I can kind of better illustrate this with a little graphic. Okay, so let's see. I'll do E1 0 to too hard. Okay, you know what? Let's okay, so this is not labeled. How do I add it? Please. I don't know how to add labels. Let me just let me copy this plot here. We'll so this is what the binomial, this is the exact binomial distribution. This is what it looks like. And this bar right here in the middle, this is centered at 50. Okay, this bar is 51. This bar is 52. And this is 53. And I'll just do every odd one, 55 and 57. And oh, this is 59. This is getting hard. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 61, 63. Ooh. All right, and we're asking 65 and higher. 65 and higher. So what I want to know is, what's the probability of being in this little zone here, and this zone, and this zone, and this zone. Okay, and basically, I'm saying, you know what? I can just draw. If I want to, I can just draw kind of like this. This is basically a normal distribution. Sorry, it's kind of hard doing this. Okay, so we're saying this is a normal distribution. Okay, and the mean for this normal distribution, the mean is equal to 50, right? And then my standard deviation is equal to the square root of n times p times 1 minus p, and that equals 5. Okay. And here, what I want to do is I want to say, all right, you know what? We're going to just call this a normal distribution. And rather than trying to figure out these exact bars and adding everything up over here, such a hard time with this, we're going to just kind of use the normal distribution and try to calculate the area of this little wedge here. Okay. All right, but where is the left edge of the wedge? Okay, where do I draw this cutoff line? Okay, so if we kind of zoom in on this little section here, I've got a bar centered at 64. So let's zoom in here, right? So here's a bar centered at 64. And then right next to it is another bar, and it's centered at 65. And then, you know, next to 65 is a bar centered at 66. Okay, and so on and so forth, right? Dot, 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 going that way. And then there's lots of bars going this way. And what we want is we want the area in this bar and in this bar. So if I shade this, right? Life is so hard. If I try to shade this area in, okay. Okay, so then where is my cutoff being drawn? It's not drawn at 65. It's drawn at, not drawn at 64, but it's halfway between 64 and 65. So I'm doing 64.5. Is that okay? I hope that makes sense. And so, so it changes. It depends on the question, right? What if the question, so what if my question was, what is the probability of getting, we'll say less than 58? Less than 50, here, no, let me change that. Of getting 58 or fewer. 58 or fewer heads. 58 or fewer heads. That will be our, let me just erase this out of the way. Okay, so 58 or fewer heads. So the coloring here, if I were to do this, I would want everything. So here's 58, and I want everything 58 and lower. 58 and lower. So what would where would my cutoff be here, right? So I want everything less than 58. Comes, okay, so we want 57 and we want 58. Okay. All right, so where should my cutoff be if we want, what is the probability of getting 58 or fewer? So here, if we zoom in on these two things, right? So I've got, here's 58. Next to 58, I got 57. Here's 59, right? So I've got a bar centered at 58. A bar, 59 is shorter than 58. These are terrible looking bars here. Okay, so here, I actually do want, I want the entire bar of 57. Oh my goodness, I don't know. Okay, I don't know how this is working, but okay. Something strange is happening here, but okay. So I want everything to the left of 58. I want everything to the left of 57 and so on and so forth. And therefore, my cutoff here is going to be 58.5. 58.5. Yeah. Okay. So depending on how the question is asked, you might go plus 0.5, you might go minus 0.5. Okay. So you have to, so I like to draw like a tiny little version of the number line with bars centered at kind of each of these numbers. And then I say, all right, do I want to shade in the column for 58 or not, right? If it says 58 or fewer, we want 58, right? If it said less than 58, then we don't actually want this bar, and my cutoff would be at 57.5. So it depends. It depends on the question. And you just have to kind of draw yourself a little picture to decide what you want. Okay, I think that's it. That's it for today. So we will end here and have a good night, and we will see you guys on Thursday. All right, thanks for coming, and thanks for being here. We'll see you guys later.